Good morning, everybody. First of all, I'd like to say that I'm very proud to be here today. As Jacobo was saying, I'm here for the 6th year at CyberCamp. We've been going around several different cities, and it's great to be here, and it's great to know that they want me to be here with them. Today's workshop is about BLE. And in this workshop, we're going to see what we can do with these kinds of devices, how we can do sniffing with BLE devices, and how we can hack, should we say, and get into the safety elements of these devices and the different scenarios that we can come across in this field. Here's a brief presentation of who I am. I work in Telefónica. I'm the director of the UEM in the degree for IT security. And there's a few other little bits and pieces there. So what are we going to see here today in this workshop? We're going to start with a little bit of a theory about BLE. I'm going to ask you a couple of questions. Have you ever taken a tool to see what the security is, or you've worked with a BLE device? How many of you? Okay, so you're going to learn a lot today, because if most of you have not worked with them, then that's a good thing, because everything that you'll see today will be something new for you. How many of you have got devices that use BLE? I think pretty much all of you should be raising your hands, because your mobile devices, your smartphones use BLE. Perhaps you have a watch, or you have locators such as the one I have here. You've got things around you that use BLE. These intelligent bracelets that you can have. And this is a good thing about BLE and doing this workshop, is that it's something that's very familiar to you. So this is a little bit of the theory. Then we'll go in the first part into sniffing. And I'd like you to be able to use what we've learned today when you get home. It's about how can I sniff into that to traffic on the network. We get to the WiSARC, and you've got a network cable, and you capture traffic. It's all about that, basically. You go to the ICP, and you see your PCAP packet, and doing this in Bluetooth at the beginning, people say, oh, I don't know about this. But we'll have a look into the different points of view of sniffing, and then we'll do an analysis of the TK. We will capture the traffic as if it were on a network, but using BLE technology, and we will analyze that traffic. So we're going to simulate a number of devices using these plaques that I have here. We'll do a number of things, and we'll work using these plaques. First of all, we'll work with a few attacks. We will attack these devices. And we'll do using a technique which is like jamming and hijacking. I can see some of you smiling, so that's good. And we'll also do encrypted attacks. So in these devices that connect to iPods or your earphones or with your watch or your mobile phone, then is that encrypted or is it not? Sometimes it is, sometimes it isn't. So how is it encrypted? And we'll have a look at those cases, and we'll have a look at what you can do in order to attack when there is encryption. We'll also talk a little bit about spoofing on devices, or what you can see with that traffic that's going through the air, shall we say. Can it be spoofed? Can it not? It seems like we've got a lot of time, but in actual fact, we need to do several tests using physical devices And we'll probably come across a few failures as well, so we'd better get on with it. So before we begin, what do we need and how can we do this at home? It's being streamed. You can have a look at this when you get home and see what we've used in this workshop and repeat it at home. So what do you need? In terms of hardware, actually I've got 3 MicroBit plaques. It says 2 on here, but I've got 3. They've got a display, some sensors, Bluetooth, radio frequency, and they've got lots of different things on these tiny little square pieces. We're going to use a Bluetooth adapter as well, a very standard one. You might have one at home. And an Android device. In this particular case, it does need to be Android, but it could be an iOS in another given case. In terms of software, we're going to analyze the traffic, so we need to be able to see the sections that we're capturing. We'll use Wireshark, HCI tool. This is available on any Linux. You don't need to install it. We do need to install BLE jack. We need that in order to be able to do the sniffing and to do a number of attacks. It's available on GitHub, and you can download it and install it right onto your plaques. We've also got PCAP. We can use it. We've got GAT tool. We've got NRF Connect. I'm sure many of you will like that because you can download that onto your mobile. You can scan and send the commands from your mobile and that people like it because it's very easy to use. And then I've got my own tool, which is Home PWN. We'll have a look at that later. So let's go to the boring part. It's 10:10. So to get you a bit woken up this morning, let's have a look at a little bit of the theory. So Bluetooth low energy. I'm going to move across here so that the camera wakes up a little bit as well. As I was saying, it's a wireless protocol, Bluetooth low energy. It allows us to connect to devices at very low consumption level, and the transfer level is lower, much lower than with Bluetooth. You can connect to a smartphone or other devices or something that has limited material so that we use less battery. This protocol was created for that purpose. There's communication on the frequency band, which is 2.4 gigahertz. Are you familiar with that? Yes, it's the one that you have on your Wi-Fi. It's 2.4 or 2.5, the Wi-Fi usually. This is important because we'll see this in the workshop. I'm going to use 40 channels, just 40 radio frequency channels. These are 2 megahertz. And out of those 40, 3 of these are ADV. This basically means that so that your devices say to everybody else, here I am. Basically, your devices discover each other using these channels. When somebody wants to connect to your device using BLE, there is a request for a connection to one of those channels. So a little bit later, we'll see that with 3 of these, we'll be able to cover all the channels and we won't miss any connection. If we miss one of them, then the device will have to go through the 3 different channels until it finds a connection pattern. We have a 66% connection, and as long as we're within the radius of the pattern, then we'll be able to make a connection. So this is all about being here, and all the rest of them are 37 channels for data. And here's a bit of a diagram to make that a bit more clear, and also in this one. So you have the frequencies down at the bottom and the channel number. They're not in order. And then it goes from 2s to 2s. in frequency in megahertz. They go 1, 2, 3, 4, and then right up to the 38. They're not in order. There's a difference between the 37 and 38. They're not together. So this is what we've got to play with in Bluetooth. This is where your device is, your mobile with your watch, your mobile with your earphones, everything that's got Bluetooth, and BLE, they all work within this different space. And the requests for connection are used through the channels that I mentioned. So how do we hop between channels then? So this is a little bit more complex. We've got channels to capture those connections. I'm here and I want to be with you. So how do we hop between channels? The data goes through the channels. They don't go through the same channels all the time. There are different hops. You are sent a number of bytes through channel 5, and then we go to 12, and then we go to 19 and 16, and there are changes of channels. That's how it works. The protocol works in this way. Down there it says there is a hop interval pattern. So how many milliseconds we're going to change channel. This is remembered in the device. And then there's an increment in the hop as well. To which channel we're going to go. If it's an increase of 7, then we'll change it to a different channel. So here you have an image to be able to see it a little bit more clearly. So here we have the frequency and the time. We can start in one channel, but you can't see the number here. Here it's in the orange value on the left. And then we go to a different channel. And in the hop interval, we're there. And the receptor and the emitter change channel. And they send data through the different channels. That's how we do the channels hop. And this is a channel map. This indicates in a connection the channels that we're going to be using. So we have the hop interval. That's the time I'm going to be on a channel. The increment of the hop, and that's where I'm going to. And we have the channel map. And I can see the flow of that connection. So it's a connection between device A and device B and the pattern that I'm going to use. And the algorithm for the channel selection is also known. This is essential for sniffing. We wouldn't be able to do sniffing if we didn't know to which channels we would be hopping to. So that's the next question, the hopping algorithms. There are two, channel 1 and channel 2. Selecting. So in BLE, we have a different version, 4.x and 5. This goes along with channel 1. And in the revision of the algorithm, there was a new version, so we have different options here, and this is quite interesting. So we have algorithm 1 with channel selection. I can copy the hops because I know this algorithm. I have the channel and the increase in the hop, and it gives me MOD 37 because there are 37 channels of data. I can't go to 38, 39. I have to go to the 37 because those are the advertisement channels. So what are the roles in this BLE game? There are several concepts. For the theoretical side, this is very important, and we have to cover this part as well as the practical side. So broadcasters, or in other words, beacons. They're used to send advertisements. When a device is visible, when it's listening to those channels, and another device wants to connect, it sends a message saying, I want to connect, using one of those 3 channels. So the broadcaster is there and sending those requests. Then we have the slave and master roles. The slave role is the one that does the connections. It's waiting there for somebody to ask for a connection and accept it. The master role does active scanning and connects the packet against the slave. And then we have the observer. The observer is listening to the 3 advertisement channels to capture that request for connection. So we have the slave, and it identifies with this scheme that you can see on here, this diagram. We can see what happens if we receive a connection or a request for a connection. I move on to connection status, and then I listen to hear to see what I can hear. So in the master role, which initiates the connections, this is what we have here on this flow diagram. So we're finishing with the theory side now, don't worry. But it does get a little bit more complicated. This workshop, I think you probably enjoy it, but when you see the part of many, many bytes, it does get a little bit more complex, but I'm sure we'll manage. So here at the top on the screen, you can see the Bluetooth layer. At the beginning, we have a preamble, and we can see a connection with the layer for the internet. So that's the part of the byte that you can see at the top. So there is a superior protocol. We've got the Bluetooth layer, another layer, and the ATT of the Bluetooth protocol is the one that we're interested in. We'll see the values that are being sent, and the devices we'll see in lower layers, and we'll also see the characteristics that are being sent. We'll see that later on. We need to know what is being sent and how it's being sent. I don't know if you're already connected with this. So now let's move on to the sniffing part. We can look at this in 2 different ways. From an Android mobile, Android because it's simpler in this case, and if we have an Android mobile, we have certain characteristics that can go through the Bluetooth from your device. And if you want to investigate or look into different types of tools or device to which you're going to connect through Bluetooth and know what packets are being sent from the mobile to the device, this is the characteristic that you need in order to identify it and pick it up. The other way of looking at it is what is the medium that is used for transmission? Yeah, you're right. It's the air, should we say. This is the means of transmission, the air. What can the air capture? And who can capture that? Anybody can. Over Wi-Fi, anything can capture that traffic. You might not be able to see it, but you can capture it. If we're in this room, for example, we can capture that. So we're going to use hardware, these plaques that I was showing you before, in order to capture that traffic that is going through the air. So these are the 2 focuses. So if I have the device and something like this, which is connected through BLE and my mobile and the app, I want to see how they connect and the commands that are being sent through so that I get the alert. Then I've got to use the application to see if it's operative and record all the Bluetooth connections, and then I can apply that and analyze it.
But if I don't have that application, I would like to know how this is communicating, then I have to sniff the traffic in RAW, and then I can find either encrypted or decrypted traffic. So Case A, just to summarize, we install the app on Android. We buy an object locator, which comes with an application, and that keeps sending different communications to the device. Then we have to activate and enable the Bluetooth HCI snoop lock, and we configure it. So everything, we can even say everything the device sends through Bluetooth, you can store in this file. And where is this going to be stored? In the internal memory. It depends on what you have, really. Now, on this device, for example, it is being stored on Android data, and the name ends with snoop.log. Even if it's a .log, this is not a text file. You take that from your device, you move it onto your machine, and you rename it, and then you open it. And that's where you see that all the communications between your mobile application and the device has been sniffed. And you don't have an encrypted layer. I'm going to show you a little example. So you can see where we can find this.
Vale, voy a pasaros el... Ahora os enseño el...
Right, I'm going to show you the PCAP so you see an example. And whilst this is loading, right. So this is an example of PCAP, where we've sniffed traffic between a mobile application that is communicating through BLE with any device. Obviously, we have filters for this. And as I was saying, what we're really interested in is the protocol, this one here. If you look at it, you can see the layers. That's what we're interested in because that's where all the data is being sent. So this is what will make a lock to open or an object to beep, for example, or the watch to do something, for your earphones to put the volume up. Everything's been done through commands on this protocol. But the same, just as it happens with TCP/IP architecture, we have a Bluetooth battery with different layers here, a different stack, Bluetooth stack, and we will look into this in more detail when we start with the sniffing. So we're just going to open this. Just a second.
Ahí. Vale, esto simplemente...
Right, so this is just to show you where you have to go, and that's mostly it. If you have Android, you go to Settings, Developer Options, and that's where you can see this that I'm showing here. So you have that option, you tick it, and once you have it, that device will be taking all the Bluetooth traffic onto a file, and from that file you will then be able to play with all that information. So just an example, I'm showing this one. So just remember that the format is going to be .log. You take it out of the Android, you use PCAP, and that's done. And then you can look at it. Now let's continue. This is very easy, and this is mostly it. Now, and the other approach, let's say we don't usually necessarily will have an attacker, and we don't necessarily know which commands are being sent from one side to the other. So what we're going to use is this kind of sniffer, like the one I'm showing, a little plate, and this is going to start listening to everything that's going through the air. So ideally, we would have 3 plates like this one. Why? Because then you would have each plate for one of the advertisement channels, 37, 38, and 39. And why would we do that? So that we can sniff all the connection packages, know that there's a new connection, and then follow it through the channel flow. So for this, we're going to use a tool called BetaJack, BTLE Jack. And with this tool, the -I option, we're going to detect these 2 plates. We're going to connect them through USB to the machine, and then the MicroBit starts working in a different way. So this is basically just adding a program so that it changes the way it functions. So first of all, we have mode 1. This is a new connection sniffing. So we can tell the MicroBit to sniff only new connections, for example. And you start listening, and on one channel, if we only have one MicroBit, it's going to have to hop until it captures it sniffs package, and we might lose some connection packages. If we have 2, we're covering 2 out of 3, so we might as well lose connections. But if we have 3 MicroBit, then we're not losing any connections. And then we have the option of sniffing an existing connection, because this connection might not be new. Data might have been being sent for a while. For example, your earphones with your mobile device. There's a constant flow of data, and we might want to follow that connection. So how do we do this? Because this connection has already been established. We have the -S option, and as you can see, -C is for new connections, and -S is for existing connections. I will show this later on the demo part, but what we will get is something like what you're seeing on the screen. And this is a bit scary, I know, because you start seeing 090F and you think, oh my goodness, what is this? Well, these are the bytes of the data part of everything that's being sent. This is the encapsulated part that we showed with the white shark. White shark is going to actually make this a bit more beautiful and make it more understandable to us. But we can actually simplify this as well, because there aren't that many bytes that are being sent, and we can identify how what white shark is saying is reflected here. Now, I know this is a bit crazier, but it can be done. Now, if you see there at the top, you see that it is saying got connect rec. So the MicroBit are on these channels I have mentioned, checking whether there's a connection package. And one of them says, hey, I found a connection package. It identifies a connection package, and it's telling you that it's traveling from this Mac to a different Mac. Now, the Mac concept here is very similar to that of an AR card. It's an ID that is created at randomly, just as it used to happen some years ago. But in some other devices, they're not created at random, but they are unique rather. Then you also have access address, which is, well, the address it is accessing from. And when you have 2 connections between devices, you have an access address to identify that connection. It's exactly a sort of identifier. Then we have CRC to see that the data that we're sending are not corrupted. You can see that we have a hop interval 24. And that means that every 30 milliseconds, there's a change of channel. So it is hopping from one channel to another. And then you can see a hop increment with a value of 6. So that means that if we going hopping channels every 6. So we're going to go from 1 to 7, then to 13, etc. And with mod 37, we can go backwards or forwards, depending on what we want. And you can see here also the channel map. And we have one FFFFF. That means 5 bytes. And if a channel is being used or can be used, it will make more noise than the others, and so that channel is going to be set to 1. So every channel from 0 to 39 are 5 bytes, right? If you think about it, every channel is a bit. So 0 if you can use it, if you cannot use it, 1 if you can use it. So you've got the map here, and as you can see, you can use most of them because there are many Fs, and that is going to change depending on the connection. And then you have the timeout as well. So as you can see, there's a lot of information here that you can check afterwards on Whiteshark as well. And how do we then put this on a file? Because everything that I have been explaining is shown on the screen, but of course there's way too many weird bytes. So how can we have this on a PCAP file? Whiteshark will allow us to do it. With -X, we will indicate the format. With -O, we will say where we want the information to be stored. And with -W, we will have a pipe to connect the telejack exit with Whiteshark. And this is very important, by the way. That and the format, the -X Nordic. And that has to be like this. So we're going to start with the practical part now.
A ver. Voy a conectar esto.
I'm just going to connect this.
Vale, ¿qué ocurre con esto? Lo voy a enseñar. A ver si se ve. Well, let's see if we can see it. This has a program, as you can see. This is simulating lock. Yeah, can you see it? Yeah, more or less. Well, I'm not very good at drawing, but more or less you can see it, right? It's a padlock. And this is actually simulating a smart lock. So instead of doing it physically, we're going to simulate it. So we have a program with a display. When it is locked, we send commands that are not the key to open the padlock, and it won't open. So we need to know which command we have to send for the padlock to actually open. So on a real smart lock, this would open when we send a command to open from the mobile application. But because we do not have the mobile application, we want to know what is being sent in order to open it. So we're going to sniff that traffic. So we come to the development environment a bit later on. Can you see this? How about now? Yeah? Okay. So we're going to connect the plates first. Remember, with -I, what we do is to put the BLE jack program to that plate automatically. So you can see they're flashing there. This starts vibrating. You can see the light flashing here, and done. Now, the next thing we can do is either wait for new connections. And because we have detected, or the application has detected, that we have 2 connections and that we also have the BLE jack, it's telling us that it has detected 2. Remember that if we have 3 microbits, we won't miss any package. Now, with another application, See, as you can see, we're already sniffing Bluetooth packages. So what we're going to do is to connect this and you can see it on the screen here. There we go. I hope you will not get to see all my messages and everything because this could happen, but well, we'll see. Well, this tool is called NRF Connect. So I think one of the things that you will take from this workshop is this application, which is quite cool. And you can see that we can see all the devices that are within our range. And on this room, we're seeing quite a lot of devices which are close to us. We have a filter here. If we want to lower the amount of devices that we're seeing, can you see 7 out of 51 at the top? So we're going to start sniffing here again. And when I tap on connect, this starts sniffing data. And if I send something, then we will be able to see it here. Is this encrypted or not? That's what we need to look into now, because this is sending it to a PCAP file, and we will see straight away whether this is encrypted or not. But you can see all the information that it's already giving us. Received connection package, origin, destination. You can see the access address, which is like the session identifier, then the hop interval, the hop increase, and the channel map. And this changes depending on the noise, because the device might say, well, in these channels there's more noise, so I'm not going to do anything here, and I'm going to move on to other channels where there's less noise. Now, this is the first step. Now, another thing that we need to be familiar with is what happens with existing connections when there's already data flow. We're going to send something over here. See, another package has arrived, another one. Now, what's interesting about this is because obviously no one around me is doing anything with Bluetooth. This is really easy to see because this connection here is sending packages. So as you can see, this is being replicated, being reused. And this is the access application, the access address. And it's the same one as this one here. Whereas in this case, we have a new one here because I have connected and disconnected. And so my connection address might change. So what we're doing is facilitating, making BTLE jacks work easier because I'm saying, well, there's a connection here. And what I want you to do is to attack this connection in several ways. So we can either keep sniffing traffic from here, or we can hijack it, which I will show you later on. So this is an interesting value. And as I was saying, we could also connect this to White Shark. So we're going to do it now so you see how it's done. Right.
So let's see what we need to put in here. In the -C, once we've got the physical direction of the objective, which is the plate that we have here, there's no random element to this. In a mobile device there would be, but not in this particular case. So we'll put this MAC in right here. We'll indicate the format. And where we want it to save the file, for example, we can say cybercamp.pcap. And this is where we're going to create the pipe. Remember, we have a pipe for the flow of data. And you can see that the BLE jack says that it's waiting for Wireshark. Let me come to the interface management section and the pipes. And I'll put in the pipe that I've just created.
Selecciono. Vale, y de momento.
I select pipe, and for the time being, there's nothing here. We'll see now when we connect. We'll connect to the same application as before. Remember, there are packets that I can lose because I've only got 2 out of 3, so there's a percentage of loss there.
A ver, un segundo.
Give me just a second.
No, se ha quedado sin batería esto.
Oh dear, it's run out of battery.
Ahora.
Okay, now we're back. Sometimes you can lose the connection. As you can see there, it says sniffing again. And it's capturing once again. And we're capturing all that traffic. We're taking it to Wireshark, and we can put it in a PCAP file. And then we can start to analyze. The analysis will do that afterwards. But right now, we can see some things here. If we do a filter using the attribute protocol, we can see that there are a number of readings, number of requests for reading and sending of data, the name of the plate, for example, or any detail being sent by this device. Because when you connect and everything is very, very clear in the MRFF connection, then you can see that there are a number of data that's transferred from one side to the other. When you connect with these skates, for example, they're so popular now, you can see that a lot of information is being sent into your mobile. There's the speed that you've been going at and the distance and so on. And all of this information goes from the sensors to the mobile devices, and that goes through BLE connection. And all of this can be captured. And you might find that in this particular case, it's not encrypted. The packet is not encrypted in ATT. It can or cannot be encrypted. So let's continue. We're not capturing commands and not capturing currently how to open the padlock, but we're going to continue and we go on to the next section now.
Bien, el análisis de PCAP. Vale.
So this is PCAP analysis. There are 2 ways of capturing that traffic, either from the app, the device, or through these plates. Using the plates, there are more solutions. There's not the only solution. There are some which are a bit more homemade, like this one, or other more complex ones. So PCAP analysis means that I have some sections and I need to know what to do with them. This is why finding out whether or not it's encrypted or not is important, because it will take me down one route or another. So what can we get from a PCAP? So we have to align in first place with a PCAP. We can get a Bluetooth profile so that we all understand it. It's what it is the description of the type of device based on its services. It says if we're connecting to a speaker or something else. And then we have the service. It defines the functions of the device. The functions of the device are the entire set of a profile. You can see that in the picture. What we're most interested in BLE is the characteristics. These are properties in the device that can give us information about the device or to send information and for it to do something. I'll give you an example. In the padlock that we were simulating, it cannot give us information. Well, it can say, I'm a padlock, I've got this series number. It can give us that information. But in order to be able to capture that information and use it in a normal application, we need notification characteristics and reading characteristics. So with the apps that we've been using and we'll look at later on, we need to be able to see the different characteristics for connection. And it'll say if it has reading or writing characteristics, both, and what you can do with those characteristics. It's setting up the context for what the device is for. If we want to send something to the padlock to open it, we have to use writing characteristics. We might send something and it might send something back in different characteristics, and we have to play with that and return with that. That's a little bit of the game that we have to play. You'll see that when you use this technology, but you need to understand what's behind it. These are other captures, other gatherings, and we've got the handler concept here, the handle concept. So I've got the 0x08 characteristic here, or the 0x0064. It depends on the application, the characteristics that you will have. So don't stop using a device because you don't understand what they're being asked for. All of a sudden you get something different to what you've used before, but it's all the same. It's just an alias of something that has come before. So we have the attribute protocol of the BLE. At the end of the day, we can read and write, but without a response. There will be an alarm, and the padlock will open, but I won't get a response. But you could have a device that indicates the quality of the air, the humidity levels, and so on, using Bluetooth. I could ask about the quality of the air at a given time. I can do that over Wi-Fi as well, but it could be Bluetooth. And if I send a request, I'm expecting a response in a different kind of characteristics. So let's move on to this slide. I said we will be able to see the information using Wi-Fi or to do it in this way. When we see this in other kind of areas, we say, oh, this is crazy. But we link it to WhatsApp, we see that they're aligned. It's just represented in a different way. But if we go step by step, we will see that what we see in WhatsApp is what we're seeing here. In the packet that we've selected, the one in the middle, the data that's been sent is 1 byte, just one. And then we have the handle, the alias for the characteristic, they're 2 bytes. You have to see that there you read it backwards. So, and have a look at the OP code as well. It's 5.2. This is a writing permission And you can get components that is a much simpler way, but you do have the IP code here. Then we have the CID. What is it encapsulating? The 4 bytes that you have on the right-hand side of the 00. This is the ATT. And then we have the upper layer. What it's saying is that this has been encapsulated, and then we have the size of the packet. They're 4 bytes, because we have the operating code on the right, and the 08 are the properties that we're working with. Remember, this is the writing. You don't need to remember this, but you will come across it, and you might find that you will say, well, without White Shark, what can I do? And what information can I get from this? If not, you can go to White Shark, and that's it. So now my watch has gone a little bit crazy. So let's go to the attack side now, the replay attack. This is the first one. We've done the sniffing. We've sniffed the traffic. We've looked at it from 2 points of view, whether you've got the app or without the app, and sniffing the air. And now what we're going to do is see if with that PCAP, that packet, if I can capture a section with the value. For example, in this padlock that I have here, suddenly it opens. A replay attack could do that. I would take that section, I connect to the padlock, and I copy it. If there's no other controls, then the padlock will open. I have a key, which is a packet, a section. I send it, and it will open. So it's as easy as that, shall we say. There are 2 ways of looking at this as well, because it can be encrypted or not encrypted. So what are most devices that use BLE like nowadays? They can use the rules of the game that they wish. Many of the devices that you use will use non-encrypted connections because it's closer for various different reasons. It will, if you sniff that air, then you'll see several different things and even sensitive information, because we capture the order that opens the padlock, and we can replicate that to open whichever padlock we're interested in. We're auditing that. I wanted to show you the made code scheme environment. This is a project in the UK, and it's very simple. I don't know how many of you know the scripts. This is very similar. It's Microsoft language. You can program it in blocks, and it can be programmed with MicroPython. You can do lots of things in this memory, and this picture of the different blocks, it represents the padlock that we were using in the exercise. First of all, it's locked. So when the plate is started, there is a closed padlock. The objective is to open it. There is another event, which is when a device connects to the plate. And at that point, what we can do is listen to what is being sent, the commands that are being sent, and there's a sniff there, and what is sent is the same as what I've got here, then I can open the padlock. If it is not sent in the same way or go through a different branch, then it will not open. It's very simple. So when it's open, we'll see a byte on the screen. With blocks, this code can be managed very easily. We download this environment on a web, and we get a .x file, And then we have to take that to the MicroBit. We set up a disk unit. I open it and paste it, and suddenly it will flash, and it will be turned into a smart lock or a simulated smart lock. I'm going to show you something else now, but even from this environment, we can say that the communication should be encrypted, and this is useful for the encrypted attack. So we have the whole environment in order to play with. So let's go now to the example. Let's see if we are able to capture that traffic or not. So let's tell the MicroBits to start capturing and send it all to White Shark. We have this here waiting.
Aquí. Voy a poner esto.
So now I'm going to connect. And one of the things I need to look at is the code, because I can't remember it right now. So I'm going to connect now.
Vale, conectado. Y le voy a mandar el comando que me abre.
I'm going to send the command that opens the padlock. H4B H PH 4F.
Vale, voy a enseñar ahora también. Ya tengo capturado esto.
Now I've captured this.
Voy a enseñar cómo queda. No, iPhone no. Aquí. El candado queda abierto.
So the padlock is now open. Okay.
Vale, y tenemos el fichero.
And we have the file. Let's go to the file. Where did I save it? It was right here, I think. We called it CyberCamp, I think.
Vale, pues en este fichero.
So we have the filter on this file from the protocol from our application. So we need to look when we get the right commands. This is a command that comes out from the mobile app to the device to do something, to write something on that device. In this particular case, the padlock to do something. And in this case, it is opening. If we have a look at this traffic, you'll see it's not complicated. We have a handle. And we also have a value. WRTX. And we've captured that. And we've done this with our own application. And we can replay that section. So without needing to sniff anything without the application, we can replay that section.
So let's do an example now. And for this example, we're going to get rid of this plate. And we're going to use another machine.
Right. So we're going to reset this. So it's locked again. See, now you can see smart lock, and then you'll see the little padlock. Yeah, done. So when this machine starts, we will see that we have a Bluetooth device, which is the one I was telling you, which was optional. If your device might have integrated Bluetooth, but in this case, because it's a virtual unit, we don't have it integrated on the device, so we need an adapter. So we're going to use an open source tool, which is called Compound HomePun. So first of all, there's a series of modules that you can fiddle with. It's on GitHub. And the first thing we're going to do is see if this has recognized our adapter, which it has. And now we're going to load a module and say that the signal doesn't have to have a very broad range. And so we're going to start scanning all the devices around here. Now, as you can see, we are detecting several devices, but we have not detected the one we were looking for. Let's just increase the range, the RSSI. It's not detecting it. Let's see. So we've got the Mac here, we've got them kind of addressed. In this case it's random, important, could be random, could be public, but we will see it straight away. And now we're going to load another module, BLE module, to read the characteristics and see its features as well. So we've got the module options here, and we give it the MAC. Now careful here, because we could manage with random or public the type of address, so we need to know which one it is. So we connect, and here we have all the characteristics, so the UID and handle. These are very important. We see the two features and the kind of permission, and this is important because if it's read-only, then it will try to download it to see what information it gives. So we have text information, and that is read automatically, but there's other kinds of information that it's not so easy to read. And by the way, in the snapshot we've taken, if I go back to my PCAP, you can see this characteristic. True that it is very long, but look at a series of bytes or something and see that they coincide with this one, which is a write characteristic. This is necessary. If we send something, it has to be write characteristic. So we copy the UID and we go onto a write characteristic module. We've got the options, the MAC, the UID. Here, when it asks for data, we have to use the code that we used before. That's here on the snapshot. 8DMN 4FBH
4F. Don't forget the encode, which could be ASCII or decimal. In this case, it's ASCII. And let's launch it. Before we launch it, let's do it this way so you can see it. Now, picture if this doesn't work, and we've been here all morning and now it doesn't work. It could happen, by the way. Ah, there we go. Now it said bye. We've done something wrong. Let's check. 8DMN 4FB H4F. It's returning a fault somewhere. I'm just checking the code again, the data. Yeah, this is returning a failure for some reason, but we have a video, thankfully, so I can show it to you anyway. Ah, now it has opened it. Let's try it again, okay? There you go. You can see the padlock. Yeah, unlock. And open. See? So this is the easiest example, because at the end of the day, it's just you capture the frame, you sniff the frame that has activated and unlocked the device, and I can just replay it. But it could happen that there's a more complex logic. For example, there's data are being sent and there's an answer and something else needs to be done, or directly that it's encrypted. And that obviously makes our intentions and objective more complicated to attain. So let's continue now. Now, replay attack is clear, right? Easy. You can do it at home with your devices, please, with your own devices, or if you're auditing another device. Right, so next attack, hijacking. Now, how many of you know the word hijacking or have seen it in some sort of attack? Where have you seen it most often? Websites? The old cookies? Yeah? Well, we have hijacking here as well. And you can see this example. Here we have the different roles that we mentioned during the theory: central, slave, master, and attacker. So this is a communication between the phone and, for example, a scooter, any device. There's a flow here, but then the attacker arrives and it starts sending timeout packets. And so this can actually have two outcomes: a jamming attack on the one hand, so service is denied and the application is disconnected from the device, and that is done through BLE jack as well. Or on the other hand, we could, instead of doing a jamming, we could lose the connection between the slave and the master, and then that's when we would come in with the access address to pretend in some way to be that connection. So that's how we manage to get control of that connection. There was an existing connection, so we've thrown away the person who was connected and we have connected ourselves. So it's completely hijacking that connection.
I've got a video here because I haven't been able to bring all the devices, but I wanted to show you what we can do with BTL Jack. BTL Jack doesn't work with every device. It depends on the implementation that's being done in the background. But I'm going to show you an example which works on this video. You'll see it later. What's interesting here is that with BTLE Jack, I have thrown away the legitimate device. I have hijacked that connection, and you can see the discover option, so I can get all the characteristics of that device and I can interact with said device. I have to know what I can send and everything, so there's a sniffing that has to be done previously. But anyway, I'm going to show you this example so you see how it works. Can you see it properly? Yeah? Right, we are activating here the session. See, there's an access address here, channel map. All these concepts you already know by now. And see here, here we are inputting the access address we want to hijack, and with -T we do hijacking, with -J we do the jamming attack. It's more or less the same, and this could take some time because now it has to get the channel map, we have to extract it because we haven't been sniffing the connection packet. So this is a previous, an existing connection. So we have to determine first the channel map, and this is what takes the longest, obviously. Then with CSE, it's actually quite easy to extract and quite quickly. There's a hop interval that has to be calculated, as well as the increment, and that is quite quick as well. But now, from here, it gives us the information. It says hijacked successful. This is all yours. And what do you do now? So what we would do here is with discover, we start getting the range 0008 to 0009, 0009 to 000E. These are handle ranges. That means that we have different characteristics which are grouped here. We don't know on which one in that range, in that interval. There might be 2, 3, 4 characteristics. We don't know. And in the end, we obtain this information that we see here. We've got permissions, write, read, only notification, only write, and the value, the handle value. And here is where we can write, overwrite the characteristic and interact with the device. But what matters here is that we have hijacked the connection. So we have thrown out the connection that the device was using, and we are in now. And with jamming, what happens is something very similar. As you can see here, instead of -T, we're going to use -J. You see it there at the top. I don't know if you can see it, but at the very top, you will see -J. And at the end of the day, this is denying service. So it is sending timeout packets as if the connection had timed out, so that the application loses connection. And now we have a different scenario. And this is the difficult scenario. So now we have encrypted connection. So this device with the mobile application is encrypted. How do we know that? Because the moment we sniff the frames, we will find out immediately. And how does this work? Information can be encrypted in different ways. It's usually through a PIN number, usually 6 digits. In a corporate environment, something more formal, the solution might be in a different kind of encryption. But you have to think that these devices usually have a very low computing capacity. So the encryption is not going to be very powerful because it would take too long and it wouldn't have enough resources. So we have the option of at least encrypting it with a PIN number, for example, between master devices. So what I'm going to show you is how easy it is to configure this case with MicroBit. And if the encryption is through PIN, we have Crackle, which is tool. You have it on GitHub, and you have to compile it on C, by the way. So Crackle cracks and encrypts BLE connections, and we get a temporary key, which is TK. So with TK and LK and LTK, we can get the short period and long period key. We need to modify something here because when we sniff those encrypted frames, we will give them to this tool. And if we have all the components, by the way, there's quite a few components we need to sniff on this frame, then we could get to the example that I'm showing you here. As you can see here, we are finding out the PIN. It says how it was done. And if I use -O here, then I get the PCAP packet already decrypted, which is cool because then we can analyze what is being sent between the two devices, even if it's encrypted. And here you have an example of the decrypted packet. So we're going to do this example, but before we do that, let's go to MicroBit a little bit, which I have opened around here. And we're going to import. Now, this is another program. This has a bit higher iteration. It's got different sensors and you can send commands. And this command goes onto the plate and asks it to respond with a different characteristic, so you don't have to subscribe or read a new characteristic. Say, for example, that you ask it to give you the temperature, the plate temperature, ambience temperature of the plate. So this game where you send request and you get an answer is full circle. But here we have a different solution, and that means that the plate, in order to pair with it, we need a PIN, and the connection is going to be encrypted. So whatever connection we make is going to be encrypted, and so we have to apply Crackle. So let's do this. So first of all, when we sniff, we have to change the format. The format that Crackle is expecting is this one, which is the raw data. Let's call this sniff CyberCamp 2, and everything else is exactly the same. It's just having this on the pipe, have an exit file, and done. Right. Oh, I need the plates. If I don't have the plates, it's going to be difficult to do this. Now, as you can see, obviously, workshops which entail using hardware is a bit of fiddling around, but well.
So now it's capturing. We can change the freeware on this quite easily when we connect the plate to the device. We have a MicroBit entity here, and we simply take it from the firmware over here. We copy it over here. Just wait a second, because we can do that so that you can see it. As I was saying, we have to connect, disconnect, connect again.
Vale, aquí tenemos la MicroBit. Fijaros.
Here we have the MicroBit. I'll just flash it up quickly. I've got the program here.
Se pega aquí.
We paste it over here, and then when we finish, we have the program, and the communication will now be encrypted. So now let's remove this one. And we'll connect the MicroBit once again. Now things are a little bit different, because in order to be able to connect, we need something. Now we need to put in a PIN. When we have an app, we need to do the pairing with the MicroBit, which is encrypted, and the connection to us. So the RF Connect application that comes up, you may have this remembered, so you have to get rid of the device. We're going to get a PCAP just like this one here when we select it.
A ver, un segundo, porque este de aquí. Vale, fijaos que tenemos.
Here we have 175 different packets, as you can see. These are all low energy levels, low energy. So we don't see the protocol attribute, we don't see the handle, we don't see anything. It's on a lower level. When we go through HTTPS onto a page, the data field is encrypted, and we see just that. We don't see the layer of the applications. So it's similar in this given case. This means that the traffic is encrypted. And here we have the connect request. And in that, we can see all the information of the channel. We can see the address for access, which channel is being used, the interval and the increments. We have the hop here. We can see all of this, and we can also see another element down here at the bottom. There's an encryption request, there's a response, and there's an initiation. So what we see after that is all encrypted. This capture is also very interesting, because otherwise the crackle won't work. We have the pairing request and the response for that, and a confirmation, and 2 pairing packets. These are the requirements. The request and the confirmation and the random. We need all of these packets in order to crack the communication using Crackle. So how does Crackle work? It's really quite simple. We insert the PCAP. We can put a PCAP output as well. And we can also put in the LTK if we've got it.
Cipher info.
Here we put cipher info. And now it's starting to crack. We could say that the workshop is coming to an end now because we really wouldn't have time to get all of that in. Maybe not an hour, but it will take quite a long time to do this cracking. But what we need to do is to know how to capture that traffic. We should have put in the -0 option. And I have the encryption package here. We had 165 packages before. Now we have the same capture here with the 175 packages. And these are all low energy layers have been converted now into ATTs because we've been able to decipher everything in these layers. In package 164 with 32 bytes of weight, we have a command and the use of the handle and the characteristic that we're sending to this command. So the program sends requests of temperature and give me information, and all of that interaction with the plate is all encrypted with a PIN. Since we haven't captured the PIN and everything we need, we have done that, and everything we need to do the encryption, we can do that. We can't do this in the workshop because we wouldn't have time to get through it all. So we have the non-encrypted layer. So we have the TMPF here sending this characteristic, and we could use that to send those commands and those requests and receive the information that we're looking for. So now that we've seen that, we're going to continue with this section here. And this is what we call about the spoofing, the impersonation. We have been looking at stealing with Bluetooth, going into a speaker that it is possible. And we can make that speaker look like a real one, or even make it connect to you. This is all about spoofing and impersonation. There was an attack that was called Dirty Tooth that was patched at the time. And this was more of a Bluetooth than a BLE issue. You could connect a speaker, and the speaker would have an audio profile, and when you were contacted, and posterior, the speaker would change the profile. You have some conditions for a profile, and all of a sudden, it has a different kind of behavior. What is that behavior? For example, is what it is able to do. What could it do? It could extract contact details. When you're going in a car, the device contacts to the car, and what would happen to your contacts. So Dirty Tooth, this is what it would do. it would allow you to connect to an audio profile, and it could extract information such as calls and contacts and so on. And this is what we're calling this is spoofing as well. It's stealing a profile, and if you're not notified, then they can take information from you. People in XY have done some research into this, and in the airdrop protocol, if you're familiar with that, I don't know. Are you? No? Does anybody here know airdrop? We know that everything else is Android. AirDrop is an Apple protocol. There was some research in which they showed very many things, and I'm going to talk about the things that we were talking about before, things that are going in the air, things that are moving around us. As you can see in the image, when we have a Mac, an iPhone, an iPad, a HomePod, and so on, we have any kind of element. I don't know if you know that they connect between each other. When you're calling, when you're being called on your phone, how does your watch know that you're being called? There's an ID that says that you're being called, but the phone doesn't have a card, but there is a communication between them through BLE, so that traffic can be sent and data can be sent. And this is what they looked into. And they came up with a number of tools. And these tools can be used to detect these statuses of the different devices, such as the Mac, iPhone, iPad, and so on. And with the status, I mean things like the iPhone has been unblocked. It's unblocked, but the screen is active. The iPhone is calling. There's a call coming in, there's a call going out, all that kind of information which travels through the air. So what is this information? It's all leaks. It's all leaks of information at the end of the day. And if we can read it, and if it's out there in the air, it can be used. You can have a look into this, and you'll see that some of the information that was sent on occasions was a hashed telephone numbers. These were difficult to capture, and you had to spoof a device in order to be able to do this. It's difficult. You could capture those hashes, and you could have a small database with I should say, but it has millions of possibilities. But it does have a plain text with all of that hash information on it. But what I want to show you is what is moving around in the air and what we can easily capture. So let me share the screen with you once again. So let me show you two things, this and this. So that spoofing of AirPods, for example, was interesting. So when you go to an iPhone, when you go near to a phone, it's like magic because you have to make the connection between the two. That's done using BLE. A BLE package is sent. Oh, and here I am. Here's the AirPod, here's the iPhone, and they make the link. It's kind of like magic, but it's just BLE, really. So BLE is more present than you think. So you can spoof this with a message. And connecting is another issue, but I can show you an example. So if you see the X-Way research, you'll have all the scripts and everything. So using the tool that we had from before, I can show you something now. For example, we can do something with the AirPods.
A ver si nos funciona. Ahí va.
Let's see if it works. Yeah, I think it's working. Has the Bluetooth connection gone in? Yes, it has, but I need to reboot the device. Just a minute. So you get the idea. We can capture everything that's circulating around in the air. We can send a notification and capture that notification of, like, I'm an airport, here I am. And I want to show you what I showed you on the presentation. The devices, if any of them make themselves available. I mentioned Mac, but in Mac, actually, they're quite random. You can change from iOS different versions. I can't remember them exactly right now.
Vale, vamos a ver. A ver si ahora nos ha pillado el adaptador.
We hadn't achieved a connection with the adapter.
Vale, ahí.
So there you have it. Simply because it's close to the adapter, it's sending a message, and the device is saying, oh, these are not your AirPods, but they need to be connected. This is just an example that information and messages are being sent through the air, mainly around status. So the investigation work that I was talking about went into much more detail. But we can also see another thing here, which is like reading the state of the devices. So now we have an iPhone and an iPad around here. They're right here in the first row. I'm changing the status. I open the screen and I block. Now it's on off. If I unblock, then it comes back to home screen. Can you see that it's being identified as an iPad? It can be a mixture sometimes. Maybe somebody might call me now. So I'm going to turn it off. So if somebody's calling, then you will see that there's a call coming in or a call going out and so on. These are all BLE packets that can be read in the air and information can be taken from them. It's all around us. And in this case, it's not encrypted because it's of little importance. But more important things are encrypted, but they are actually leaks, of course.
And yeah, just almost we're drawing to conclusion. We're almost done. And let's just talk about what we have to take from this workshop. There's a lot of fiddling, there's a lot of hard work. Some of you will like it, some others will prefer software and not really like this because you don't like to fiddle around with stuff. I understand. Whereas some others will say, oh, no, I really like this. I want to start with BLE. It's really interesting. There are really cool tools. So it's just a matter of having some clear conceptions and it will be easy for you to grow on this. And the first thing that you have to take from here is that encrypted connections, when there is sensitive information, and it's usually the case in this kind of devices. We were playing with a simulated padlock, but could you picture if this happened with a device that has, say, for example, health data? and that information is just traveling freely around the air. So that is sensitive information, and it is, or it should be, much more protected than other things. Now, it really also depends if this padlock was a real padlock, on where it was for it to be more or less sensitive. Now, you can do replay if the data are fixed and not variable. So we were talking about sniffing data, the value was always the same, and then it did something when it identified that value. This could be interesting, but you would need to study the logic of that application. It's reverse engineering. You can always do hijacking, which is a bit like jamming, a little service denial, and then you can spoof that access address and read characteristics or send commands through those characteristics. Now, main concepts we've seen, channel map, hop, how BLE works, in which channels it is, the characteristics, because at the end of the day, we all depend on them, be it to write or to read for different devices, because at the end of the day, the connections that you're going to scan are connectable. But of course, you need to know how to work with them, know the logics, know the security of those devices. And then you have to also take from here that you can break the encryption with an EC 6-digit PIN by sniffing everything that's necessary. For example, in WAPA2, you had to sniff the handshake so you could crack it. And this is very similar, but with pairing. And also with the data is encryption starting. Yes, it is starting, and then you get a temporary password, and then you get the long-term and short-term passwords, and you can decrypt the packet. So this is a quite new world. It is true that there are many people who are developing a lot of devices on BLE. And as I was saying, in this field, there are many companies that do more or less what they want, really, because they program and they code things the way they want, and sometimes they think about security, and sometimes they unfortunately don't think about security. So these tools are going to allow you to audit at least your devices. Please also make sure that you respect the rules of the game and that you do not go over anything that you shouldn't go over, and don't do anything you shouldn't be doing. But for example, there are companies which are already hiring people to have BLE audits to see if their wireless communications are secure, if their application's logic is secure as well for transmissions. So obviously this is quite present nowadays. So I think this is all from me. I just wanted to share with you a few interesting links, especially for those of you who are following us on streaming, so you can follow this again. The video, I think, will be available from tonight onwards. So if you have any question now, the previous slide, yeah? You will find the video afterwards, don't worry. Okay, thank you. If you have any questions, just let me know. There seems to be a question over there. Well, first of all, thank you for your presentation. Sorry, I couldn't see you. There you are. You've shown a flow chart when you were talking about hijacking, and there was a smartphone and a BLE device. I was wondering, the applications that communicate from the smartphone with the BLE device, they usually also have HTTPS connections against an API. You mean on Wi-Fi? Yeah. How would you approach a red team audit when there's an API, a smartphone, and a BLE device? What would be the objective? Because it depends. For example, if you do reverse engineering of the communication protocol of all these devices, be it the API, the smartphone, or the smartphone with the BLE, the API can send requests to the smartphone, and this in turn send message to the BLE device.
So what you're saying is that you get orders through HTTPS to the application, then through the application to the BLE against the device that we want to control or we are controlling. Right, so HTTPS would be more strengthened, so we would first of all analyze that. But the weakest link here would be when you connect the device to BLE, because if that connection is not encrypted, then you would attack the BLE part, because you can see what's being sent through HTTPS. But if the application is a bridge, as you were saying, the device is a bridge, and what I get through a Wi-Fi channel, I am sending or resending through another channel. And if this is not encrypted, and by the way, PIN is not necessarily secure, but if you pair once, then they have to sniff your pairing. Because when we talk about decrypting, we talk about sniffing the pairing. But anyway, if the BLE channel is not secure, then those commands that are being sent through HTTPS, you would attack that. And especially if you are red team, you have 3 vectors: digital, physical, and social, or social engineering human factor world. So you would have to go to the most physical side. You would have to be close to that communications, because that would be the weakest link. And that's where the attacker would look for. Okay, and I have another question, please. So, for example, we are studying the communication protocol, and we infer from that the flow chart and the status chart. But there is one thing within BLE devices, such as scooters or bicycles, there's usually a SIM card. So, and that's what we didn't really get. Because that side, which is a telecommunication side, how would you audit that? You mean for the SIM card, right? Well, we would have to really see what type of communication is being established, see if it's 3G, GSM, 4G. So depending on the type of communication, we will need which tests we have to associate to each, because obviously 4G has higher security. So we need to run some tests, and we would have to choose a methodology for those tests and then start from there. So if I have understood correctly, is the same scenario that we had before, but with a SIM card, with an added SIM card. So just take into account that the channel, if you're coming out through a mobile network, a 4G network, you are getting traffic, HTTPS traffic. And let's say it's robust and that there's no weaknesses. So it would be the same thing, because the weakest link would be the connection with BLE. How are you going to audit that then? Then you would have to, first of all, determine the encryption that the mobile communication is using, with which layer, 3G, 4G, GSM, and that's where you can run a series of tests as well, because obviously that could be a weakest link as well in that layer. Thank you very much. Any other questions? There was one here. Hello? Yeah. My question is, if you are under attack, it depends on the device that's being spoofed, or depending on that device, they will get different information, right? Yeah. So from that attack, how much information can the attacker get, or what kind of information can they get? Pictures? It depends. For example, with Dirty Tooth, and by the way, if you don't know it, have a look at it. What they did was to spoof a speaker, and it was an audio profile, and you could hear music. This was Bluetooth, not BLE, by the way. Then they would change the profile, and it will become a hands-off device. And hands-off devices have different functionalities, such as, for example, extracting your contacts and your call logs, and even the devices that were on your contact list. So there they could do that. But on the examples that we've been seeing, which is sniffing raw traffic, and then we have to apply the different layers with Whiteshark to see exactly what we are sniffing, and that's what the what is complex. So when we are sniffing
stuff through our mobile application, then we have an advantage because we have the application ourselves, we know what we're doing, and then we can interpret that traffic because we see, oh, I've pressed this button and then this has been sent through Bluetooth. So we see exactly what can be extracted. But it really depends on how you approach it. So if we're talking about spoofing and if that device has trusted you, anything that you can extract in terms of functionalities from that device can be more or less, it really depends. But with Dead2, for example, it's contacts and call logs. And say I spoof a scooter. Can I then use a different profile? Can I change the profile? No, that is a different thing. Say you spoof AirPods or headphones. Not even spoofing them. I think we are mixing up spoofing and hijacking here, yeah. If you hijack a headphone connection, then you can maybe turn the volume up or change the song. So depending on the device and its functionalities, then you can do more or less things. Thank you very much. Any other questions? No? I think we're almost done then. Oh, there we go. There's another question. My question is, can we sniff BLE modules with a normal or classic Bluetooth module? Yeah. You mean maybe not with every module? It depends on the characteristics of the device. These little plates are thought for something else, but you can do it with these plates. But with this device that I've got here, the little one that I've brought, it depends. It depends on the features. It depends on the Bluetooth version. It has to be 4.0 or higher because BLE is from 4.0 or higher. But if it's older than that, then you won't be able to do it. Thank you. Any other questions? I thought there wouldn't be questions, and there are loads of questions. Hi. First of all, thank you very much for this presentation, and picking up from what my colleague was saying, because we've been doing some research on scooters, motorbikes, etc. And as he was saying, obviously there's a possibility of having more secure connections via different media. And I wanted to ask you, have you ever worked with smart locks? Because I infer that in that case you don't have that possibility, or do you? Because if you, say, have an inhibitor, a 3G inhibitor, for example, then that person couldn't be able to get into their home, for example, unless they had something. So are those smart locks more centered on BLE protocol? Well, yeah, we can find that kind of smart locks, yeah. But there's a group of smart locks that are definitely focused on this. And how do they do it? Well, the protocol could be encrypted, of course, or it should, really, because obviously this is something quite sensitive, because our example was quite easy and it was encrypted and then decrypted. It will depend on the computing abilities of the smart lock as well. We know that the PIN is not secure, but then obviously you have to take into account pairing, sniffing, and many other considerations. So it's almost being at the right time in the right place. But then how this can be applied, it's very different. This channel can be strengthened and it can become something just like HTTPS in a different environment, for example. Yeah. Thank you. No more questions? Okay, well, thank you very much.